All right, everyone, let's go over this week's assignment, the SPSS one-way between subjects ANOVA. So the goal here was to compare final exam scores across 3 different hours of studying groups, 0 to 2, 3 to 5, or 6 plus. The research hypothesis we're testing is, do the final exam scores differ according to the number of hours studied? So what this hypothesis does not say is people who studied more did better, or something like that. It's not directional. This is a two-tailed hypothesis. So first question is not meant to be um, a misleading question. How many levels of study hours are being compared in the ANOVA? We got 0 to 2, 3 to 5, and 6 plus, so there's 3. Is the research hypothesis above the one we just talked about, one or two-tailed? It is two-tailed. How do we write two-tailed hypotheses? Well, they're always written like this for ANOVA one way. So we have the mean of group 1 is equal to the mean of group 2 is equal to the mean of group 3. And so where would we be right? Well, if those things aren't all equal to each other. Why? Because that would support that final exam scores differ according to the number of hours studied. So equals, not equals. So we got to test the normality assumption. Many ways to do that. I suggest you do descriptives and go over to descriptives and then go down to explore. We'll put study hours as our factor. It's our independent variable. Final exam scores are dependent variable. And under statistics, we just got to make sure we're getting good stuff. I think it comes default as part of just descriptives. So we click OK and we click OK. So remember, the rule for things to be basically normal is that the absolute value of the skewness coefficient has to be 2 or less. So let's go ahead and take a look at them. So for group 1, the skewness coefficient is negative 0.199. That is not greater than 2, so we would say basically normal. 3 to 5 hours, the skewness coefficient is also not 2 or bigger. And for 3 to 6 hours, it is not 2 or bigger. So we would say all 3 of these are basically normal. So the exam scores for all 3 groups are approximately normal. So do these data meet the normality assumption? Well, yeah, because that is the assumption that the groups are basically normal. So yes. So now we're going to actually run our one-way ANOVA. That's under Analyze, Compare Means and Proportions, and One-Way ANOVA. Our dependent variable is final exam score. Our factor, that's your independent variable, is study hours. Under post hoc, this is where if this thing is significant, all you know is that at least one group differs from the others in their final exam scores. So we use Tukey, which is right here, to get follow-up tests that do mean-to-mean comparisons, find out which groups differ from which specifically. Under options, do I tell you guys get a mean spot? Good, because I get a mean spot. You want descriptives, and you want homogeneity, and you want mean spot. Descriptive, homogeneity, mean spot, continue, and okay. All right, so here is the results of our one-way ANOVA. First thing I asked for is means and standard deviations. So for 0 to 2 hours, that is this group right here, the mean numbers of hours, our mean exam score is 88.40 with a standard deviation of 7.56. 3 to 5 is 94.50 with a standard deviation of 4.65. And for those who studied 6 or more hours, the mean score was 81.50 with a standard deviation of 8.95. And that is what these say. So now we have to check the homogeneity variances assumption. To do that, you go to test of homogeneity variances. The line that says based on mean, you go look at the sig. As long as that sig is greater than 0.05, you have met the assumption. So you don't want this to be significant. And using alpha of 0.05, does data appear to meet the homogeneity variance assumption, i.e. is Levine's based on mean sig greater than 0.05? Yes, 0.154 is greater than 0.05, so these data meet that assumption. All right, using alpha of 0.05 in the decision rule, should the omnibus null hypothesis be rejected? Here's our actual ANOVA results. We go look at this between groups. Between groups is whatever the independent variable is, which in this case is the 3 groups of hours studied. Skewed on over to sig. Sig is less than 0.05, so we would say yes. We would reject the null hypothesis that all groups are equal to each other. So this hypothesis right here, that the means of all groups are equal to each other, is rejected. So that means at least one differs from at least one other. So 5 is yes. Let's see. So all that has to be the case for you to fully reject null hypothesis for a one-way ANOVA, they're always two-tailed, is significance is less than 0.05. So for number 6, you would say yes. Yes, we reject the null. So why is that? Well, the sig is less than 0.05. That's all that has to be true. Scooting on, we're going to calculate the proportion of variability in the dependent variable that's accounted for by its relationship with the independent variable. To do that, you follow this little formula right here. Sum squares between groups I of E divided by the sum squares total. So I'll bust out little calculator. And we need sum squares of between groups I of E. Which is, oops, I covered it. There we go for me. 846.067. 846,067. And we want to divide that by the total, which is 2275.467. So 224.75.467. We get 0.3718, blah, blah, blah. If you round this, it rounds to 0.37. So hopefully that's what this says, 0.37. Now we got to use this general format for reporting APA results for ANOVA and fill it in. So we need between and within groups dependent variable. The actual F value itself, we have to choose P less than or greater than, and then we already put our eta squared we calculated right there at the end. So we have an F with 2 and 27 degrees of freedom. That's equal to 7.99. P was less than 0.05, and eta squared is equal to 0.37. That's where all this came from. The next thing is to go ahead and fill in an ANOVA summary table. So ANOVA summary table is this table, but put into APA format. So we've got 846.07, 1429.40, 2275.47, 2, 27, and 29 degrees of freedom. Mean squares, 423.03 and 52.94. Our F value rounded to 2 decimals is 7.99. It is significant, so it gets a star right there. It's got a little star, which means P is less than 0.05. And then finally, eta squared, we calculated up above, is 0.37. That goes here. That's ANOVA summary table. So number 10 says, given that we rejected the null for this omnibus ANOVA, what can we conclude at this point? Well, because, or at this point, let's go look at what we've concluded, because that's our alternative hypothesis. We've concluded that the mean of group 1 is not necessarily not equal to the mean of group 2 is not equal to the mean of group 3, that there's at least one difference. To figure out where that one difference actually is, what we do is we use, so the conclusion is at least one of the groups performed better on the exam than at least one of the others. So for number 11, this is where we get the nitty gritty. What is our actual mean to means comparisons? That is where you go into Tukey. So post hoc tests, Tukey HSD. What this does is it compares each one of the groups to each of the other 2 groups. So it kind of repeats itself, so we have to find the ones that are unique and individual. 0 to 2 versus 3.5. 0 to 2 versus 3.6 plus. And then finally 3 to 5 versus 6 plus. Those are the 3 unique ones. All right, 0 to 2 hours versus 3.5 hours. Did they differ? 0 to 2, 3.5. Sig here is not less than 0.5, so you would say, nope, there's no difference. They're essentially equal. Then we have 0 to 2 versus 6 plus, 0 to 6 plus. Is that significant? It is not. So we would say that those who studied 0 to 2 hours and those who studied 6 plus hours are basically equal on their midterm scores, not sig. Finally, for 3 to 5 hours versus 6 plus hours, that's 3 to 5 versus 6 plus hours. That one's significant. So the question is, all right, so who did better, those who studied 3 to 5 or those who studied 6 plus? To figure that out, we got to go look at our means. There's our mean. So it's 3 to 5 versus 6 plus. We know that 94 and 81.5 differed. Who did better? The 94.5. So what's going on if the 94.5 had a higher mean average? Now what we need to do is put it all together, and that is the what would you tell your grandma if she asked you about your study? So we know that 0 to 2 scored about the same as those who studied 3 to 5. 0 to 2 also didn't differ from those who studied 6 or more, but those who studied 3 to 5 hours performed better than those who studied 6 plus hours. That is what this says. Those who studied 0 to 2 hours did not differ in exam scores from those who studied 3 to 5 or 6 plus. That's these two. However, those who studied 3 to 5 hours scored higher than those who studied 6 plus hours. The other way to do this is once you identify from the Tukey which groups differ from each other, you can go look at the means plot. So, okay, this mean, whatever it is, on exam score, 88 something, 89, did not differ significantly from that one, did not differ significantly from that one. However, these guys scored higher than those guys. Why is this not different? Well, it wasn't significant, so it wasn't a big enough difference that it made a difference. Final thing, if the data had been instead ordinal, severely violated the homogeneity variance assumption, or the sample sizes were very small and unequal, what backup test could be used instead? So to answer that, we got to pull up our matrix of significance, our statistical tests. We got to find the one that is directly above one way between subjects ANOVA. What's above this one? Kruskal-Wallis H test. That is the test you can do even if you severely violate the assumptions. Kruskal-Wallis H. And that's what it says right here. So hopefully you wrote it up. It wasn't too bad. And hope this was useful for you.